how we're going to think about communication links for the rest of the semester. A link budget is an accounting of power levels at different parts of a receive chain. So for the receiver pictured here, it would be a spreadsheet that tracks the values of each of PTX, PRX, P1, P2, and P3. Keeping this document lets you make important design decisions, like how many amplifiers to use in the receive chain. It also lets you predict important performance parameters of the system. One crucial example is sensitivity, which measures the smallest signal you can receive. Finding the sensitivity requires us to analyze the electrical noise in our system, so we'll be developing a theory over the next few weeks of how much noise your system generates. Another important parameter is the maximum power our system can tolerate, and finding that maximum power requires us to come up with a different theory about nonlinear behavior of amplifiers. These two design parameters define a maximum and a minimum acceptable signal, and the ratio of those maximum and minimum signals is called dynamic range. Dynamic range is the king of specifications for many analog systems, and we'll care about it in this class too. So here's a simple example. We assume we're transmitting a 10 dBm signal at 3 gigaradians per second from an antenna that is 10 meters away from our receiver. We've noted that our transmit power is 10 dBm on the left, and then as it propagates to our receive antenna, it goes through some path loss. And note that we're ignoring the transmit and the receive antenna gains in this example. So we calculate the path loss is minus 66 dB. That means the receive antenna picks up minus 56 dBm of power. There's 10 dB of gain on our first amplifier stage, which means P1 is minus 46 dBm. Then the insertion loss of a bandpass filter reduces our power to minus 47 dBm, and another amplifier gives us a final power level of minus 17 dBm at the analog to digital converter. That value is important to know. It lets us answer questions about the ADC, like how small should the least significant bit be, and what should the sampling frequency be. Even with this simplified model that ignores components like filters, TX-ARC switches, and mixers, and even though that we're ignoring noise and linearity, we can still get some interesting information. As we add details to this model over the next few weeks, we'll get even more interesting information. When we're making link budgets, we also have to think about undesired signals. This image depicts a type of undesired signal called a blocker, which is a very high power signal that has a frequency near our desired signal. The classic example is if you're on Wi-Fi and someone turns on a poorly designed microwave. Both Wi-Fi and microwaves live in the crowded 2.4 GHz unlicensed industrial, scientific, and medical band, which is often abbreviated ISM. But microwaves throw out kilowatts of power, while Wi-Fi signals can be quite weak. I've sketched an example spectrum of a blocker above the receive chain, by the way. This might be what your PRX looks like. A blocker like the microwave can overload the amplifiers, which causes the whole receive chain to fail. That means when we make our link budgets, we often need to make them at multiple frequencies to assess how the combination of filters and amplifiers that we've picked works for blocker signals in addition to signals in our frequency of interest. It also means that the linearity and distortion behavior of the receiver can be just as important as the noise behavior, especially in congested wireless environments. So in summary, a link budget is an accounting of signal power, noise power, and distortion power at different parts of a signal chain, and blockers add complexity to a link budget, requiring more frequencies to be considered.